start today's class. So today at first we are going to solve this numerical. So for solving this numerical at first we are going to assume z equal to x plus iy. Then what will be z bar equal to? Correct, x minus iy. Now at first we are going to assume that z tends to 0 along x-axis. Then what will happen? Y equal to 0. So limit z tends to 0, z bar by z will be equal to limit x tends to 0, x by x equal to 1. Again, we are going to assume that z tends to 0 along y-axis. Then what will happen? X equal to 0. So, limit z tends to 0, z bar by z will be equal to limit y tends to 0 minus iy by iy equal to minus 1. So, since both the results are different, so what will happen? The limit will not exist. Now for solving this question also at first we are going to assume z equal to x plus iy. Then what will be delta z equal to? Delta x plus I delta y. And what will be delta z bar equal to? Delta x minus I delta y. Now we have to find the dz of z bar. Now this is equal to limit delta z tending to 0 f of z plus delta z within that bar minus f of z by delta z. Now this is going to be equal to limit delta x tending to 0, delta y tending to 0, f of z plus delta z. Then it is equal to x minus iy plus delta x minus I delta y minus x plus iy by delta x plus I delta y. Now this is equal to limit delta x tending to 0, delta y tending to 0. This will cut each other, this will cut each other. So what we have? Delta x minus I delta y by delta x plus I delta y. Now if delta y equal to 0, then the required limit is limit delta x tending to 0, delta x minus I delta y. Sorry, this is going to be 0 because delta x we have assumed that it is equal to 0, equal to 1. Again, delta x equal to 0, if we choose that, then the required limit is limit delta y tending to 0 minus I delta y by I delta y equal to minus 1. So since we are getting different result, the limit does not exist. Sorry, here this is going to be f of z plus delta z. Because here it is given that f of z equal to z bar. So, f of z plus delta z equal to this because there is one bar, and f of z equal to this. Now we are going to solve this numerical. So here it is is given that w is a function of z in which form 1 plus z by 1 minus z. So, dw dz is equal to ddz of f of z equal to ddz of 1 plus z by 1 minus z. Now this is equal to 1 into 1 minus z minus 1 plus z into minus 1 by 1 minus z whole square. That is simple derivative actually. So 1 minus z plus 1 minus z by 1 minus z whole square equal to 2 by 1 minus z whole square, and f of z is non-analytic at z equal to 1 because at this point derivative of the function does not exist. Actually, this is the singular point. Now we are going to prove this. So in order for f of z to be analytic, the limit delta z tending to 0, yes, f of z plus delta z minus f of z by delta z equal to f dash of z equal to limit delta x tending to 0, delta y tending to 0, u of x plus delta x comma y plus delta y plus iv of x plus delta x comma y plus delta y minus u of x comma y plus iv of x comma y by delta x plus I delta y. This must be independent of the choice of how delta z approaches 0 or delta x and delta y approaches 0. Now in case 1, we are going to assume that delta y equal to 0. Then what will happen? Limit delta x tending to 0, u of x plus delta x minus u of comma y minus u of x comma y by delta x plus v of x plus delta x comma y minus v of x comma y by delta x. Here this is I. So now this is equal to del u del x plus I del v del x. Now in case 2, we are going to assume that delta x equal to 0. Then what we get? Limit delta y tending to 0, u of x comma y plus delta y plus, so here minus u of x comma y by I delta y plus v of x comma y plus delta y minus v of x comma y. I will cut each other, so we get this, and this is finally equal to del u del y, here there will be I plus del v del y equal to minus I del u del y equal to del v del y, sorry, plus del v del y. And what we got earlier, that del u del x plus del v del x. Now if f of z is analytic, these two must be actually identical. Del u del x plus del v del x and minus I del u del y plus del v del y must be identical. That is del u del x equal to, this is the real part, so del v del y, and if we equate the imaginary parts, what we get? Del u del y equal to minus del v del x. Hence the theorem is proved. This is actually necessary condition for this to be CR equations. Now if f of z is analytic in R, what we know? We know that the CR equations, that is Cauchy-Riemann equations, del u del x equal to del u del y and, sorry, del u del x equal to del v del y and del v del x equal to minus del u del y are satisfied in R. Now we are going to assume that u and v have continuous second partial derivatives in R if we differentiate let's mark it 1 and this 2. 1 and 2 with respect to x and y respectively, we get del 2u del x2 equal to del 2v del x del y and del 2v del x del y, sorry, it is going to be del y del x, and since here it is continuous, so we know del x del y and del y del x both are same, equal to minus del 2u del y2, that is del 2u del x2 equal to minus del 2u del y2, that is del 2u del x2 plus del 2u del y2 equal to 0. That is U is harmonic in R. Now similarly, differentiating 1 and 2 with respect to y and x respectively, we get what we get? Del 2u del y del x equal to del 2v del y2 and del 2v del x2 equal to minus del 2u del x del y. That is del 2v del x2 equal to minus del 2v del y2. That is del 2v del x2 plus del 2v del y2 equal to 0. So what we have proved again? That v is harmonic in R. Hence proved. So that's it for today. We are going to meet in the next class. Till then, bye.